All things quantum begin with Planck's constant, but to understand it, we must first know a few things. Let's get started.
A black body refers to an object that absorbs and emits all radiation at all wavelengths. While perfect black bodies do not exist in nature, we can get pretty close. Here's the idea. You start with the dark colored box and radiation of various wavelengths enters through a small hole. The radiation will either be reflected or absorbed as it makes contact with the walls of the container. Over time, all incident radiation will be absorbed and emitted. When a black body is at a temperature uniform with its surrounding, its emission, called black body radiation, has a characteristic distribution between wavelength and intensity. British physicists Lord Rayleigh and Sir James Jeans sought to find a mathematical model to fit the black body radiation data, according to the laws of classical physics. Here's what they came up with. As you can see, while the Rayleigh-Jeans law accurately predicted experimental results at large wavelengths, its predictions varied drastically from the experimental results at small wavelengths. From their equation, we can see that as the wavelength approaches zero, the energy per unit of volume is predicted to approach infinity, which is physically impossible. This inconsistency was referred to as the ultraviolet catastrophe, which ultimately revealed that something fundamental was missing from our understanding of light. In 1900, German physicist Max Planck theorized that light energy is quantized. That light is transferred in small, discrete packets of energy rather than in a continuous wave-like manner. He called each packet of energy a quantum, the smallest possible unit of energy. Planck knew energy is directly proportional to frequency. To connect the variables, Planck realized that there must be some constant h that can be multiplied with the frequency to determine the energy of a quantum, like so. This h can be thought of as a slope, like m, and y equals mx. Think about it this way. Let's say this graph represents a linear relationship of energy and frequency. Like any line, there should be some common ratio, or slope, between any 2 points. In this case, Planck's constant is the slope that connects the energy of a quantum to its respective frequency. So, if we divide any change in energy with its corresponding change in frequency, we can derive Planck's constant. Through precise experimentation, Planck's constant was determined to be approximately 6.626 times 10 to the negative 34th joule seconds. This revolutionary constant has allowed us to learn about the quantum realm. With the help of Planck's constant, we can now find the energy of a quantum. It logically follows then that we can find the energy of quanta with E equals nh nu.
Let's visualize what this means. When I climb this ladder, I can only go up by climbing one whole step at a time, and all the steps I take are nothing but multiples of the lowest step. I couldn't possibly climb 2.5 steps. This is why all energy must be whole number multiples of the smallest possible unit of energy, h nu. We realized the importance of Planck's constant in 1905 when Albert Einstein proved the existence of photons, the physical particles corresponding to h nu. Planck's constant ultimately laid the foundation for modern physics on the quantum scale and will continue to inspire breakthroughs for generations to come.